What is a derivative? Quick, any thoughts? Right or wrong, doesn't matter. Go for it. Aishka, what do you think about derivative? See, why I ask these questions, I could straight away given you the formula here and I started off, right? But then at times it doesn't work. The question could be application and they could ask you, give me the slope of the tangent at this point on the curve. You don't know, for example. But then they asked you derivative, as simple as that. So what is derivative? I gave the definition in here.
The tangent to look at a point.
Slope of the tangent to a point on the curve. So derivative is the slope. Basically, it's the slope. Right, Romel? Derivative is the slope. And slope is what, Chris?
Gradient.
Slope is gradient, rise over run. Change in x over change in y. So can I say change in x, x2 minus x1 over, change in y, y2 minus y1 over x2 minus x1. Rise over run. And in the world of calculus, I call y2 minus y1 as delta x, so delta y over delta x. Delta is the change. Yes? And this delta can be written like this. I'm writing x on top. Or dy by dx. They're all similar notations. All similar notations. This is what it is. It is the slope. Slope of what? Slope of a tangent. Tangent, what is tangent? Tangent is that line which touches the curve at one point. One point. Yes, Romel? So if you've got a curve like this, and I say, okay, that's the point, draw a tangent. So that's how it's going to be, right? Sorry, not a great one, but this is how it's going to be. It's going to touch a point. And I'm going to find the slope here. The slope here, slope of this tangent to a point. Right? This looks to be a negative slope. Right? And if it is like this, and I say, okay, find the slope here. So probably I'll touch it and go, okay, the slope was negative here, the slope is positive here. Right? Because the tangent looked like this, now the tangent looked like this. What about this point? The tangent is flat. So the slope is 0. So at the turning point or at the stationary point, the slope of the tangent to a point on the curve is 0. Right? If I build it, you could have a curve like this. A cubic curve. So if I say, okay, give me the tangent here, give me the tangent here, give me the tangent here. So tangent at this point could be like this, a positive. Tangent at this point, positive. Tangent at this point, 0. So positive, 0 positive. Sign did not change. So this is also a stationary point. I call this point as point of inflection. So what is the difference between a turning point and point of inflection? So I've gone really ahead, right? But then since it's connecting the dots, I thought probably I'll talk about it. Is when your slope does not change its sign after it has hit the stationary point, it is called point of inflection. Positive remained positive even if it's hit 0. Yes, Ayushka?
Yeah.
And here, negative, 0, positive. It flipped its sign. So this stationary point is called turning point. Does that make sense? Does that make sense? Yes? Cool. Now, I also call the derivative or the slope as rate of change. Another verbal, sorry, synonym, basically a synonym, not verbal, another synonym of derivative. So someone would ask you, find the derivative, find the slope, find rise over run, find dy by dx, find delta y over delta x, or find rate of change. They're all talking about the same thing. But this rate of change for derivative, you've got a special word attached to it called instantaneous rate of change. Instant rate of change. Instant means your rate of change could be of two types. Aishka, do you know what that is?
I kind of remember from last year.
Yeah, so I'm just brushing that up, right? I'm just brushing the dust off. The first one is called the average rate of change. And the second one is called the instantaneous rate of change. Okay. Let us say that you've got a curve like this, right? Now, if that's the point P and that's the point Q, you need a glass of water, Chris? You're fine?
Yeah,
Tired?
I'm fine.
Tired?
Yeah,
I know it's going to be a tiring day. Yeah. I'll try as much as possible to wake you up. I know evenings after schools are tiring. Yeah. Sorry about that. It's okay. So, if I were to find the average rate of change between the 2 points, so for average rate of change, I need 2 points, start and the finish, right? P is the start, Q is the finish. So I draw a line, let's say this was Q, right? Let's say this was Q. I draw a line, and let's say this point is A and this is B. And let's say this was a function f of x, the y basically, right? So what would be this value here? F of A, right? F of A, right? If x is a f of A. And this value would be f of B, right? So this coordinate would be f of A comma A. This is f of B comma B, right? Rebel, yes? Now, if I were to find the average rate of change, I just need to find the slope. That's it. y2 minus y1 over x2 minus x1. y2, did I flip it? It's a comma, you didn't correct it, right? A comma x is this, right? And b comma f of b, right? So y2 minus y1 over x2 minus x1. So shall I say f of b minus f of a over b minus a? That's the average rate of change. Yes? Make sense? Now let's say let's see, how do I derive or convert the average rate of change to the instantaneous rate of change? Let's say I bring this Q, or probably I bring this P here. Now, so I say, okay, find me the average rate of change. So you say, all right, I can do that. That's the line. Correct? And you will find, again, there's some value of y, some value of y here, and the same thing applies. Right? Now, let's say I bring this point here. And I say, now P is here. Forget about this one. Find me the rate of change, average rate of change. So you'll say, all right, I'll draw another line, connecting the two dots. Again, the same story. Now let's say I bring the 2 points very, 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 very close to each other, so that with the naked eye, they look just 1 point. That means if you round it off, let's say they are so close to each other as in 0.00000000001 centimeters apart from each other. So with naked eye, you'll say there's the same point, right? So now if I draw the line between the 2 points, what will happen? Don't you think it will appear to be a tangent at a single point? Right?
Yeah.
So now, when your distance between the 2 points is negligible, it says if your distance between the 2 points, if the distance between 2 points approaches 0, not equal to 0, approaches 0, then it appears that the 2 points are one on top of the other. And then this was a chord, right? You see the circle? The circle, or probably the line that joins the circle at 2 points is a chord, like a diameter, right? So now this diameter or this chord has all of a sudden started to look like a tangent because it's touching at one single point. Appears to touch. Why? Because the distance between the 2 points is approaching 0. And hence now I am finding the rate of change literally at one point. That's it. Why? Because the distance between 2 points is literally 0. Not a 0. Almost 0. Not a 0. So this kind of scenario is called instantaneous rate of change. That's how your average rate of change becomes your instantaneous rate of change. So, how do I write? So this was my average rate of change formula. Now, what is the instantaneous rate of change formula? Instantaneous rate of change is very simple. It says, okay, if you've got f of x plus h minus f of x over x plus h minus x, where your h, I say limit, your h tends to 0. Have you heard about first principle in differential? This is what first principle is all about. Now what is h? You can ask me. H is the distance between the 2 points. The distance between the 2 points. This is h. So the moment we've started to bring this p closer, this h started to go down. Yes, Romel? And finally this h, if it's this value, I can say my h is 0. Right? And that is what it says, limit. I'm limiting, putting a limit, that my h is 0. So this is called the instantaneous rate of change, or shall I say, the first principle derivative. First principle derivative. Does that make sense? 100%?
Yeah.
I thought it was 2h.
Hmm?
You know, for the bottom.
Yeah?
Yeah, in year 11, was it? I think we did it as like 2h.
No.
No?
Eventually, your x and x will cancel. So it will become f of x plus h minus f of x over h. Limit h tends to 0. This is your first principle. So Romel, what we just discussed was average rate of change was when the distance between the 2 points is very significant. So you actually just apply the formula straight away, the Stokes formula. But instantaneous rate of change is when you start to bring the 2 points very close, literally on top of each other. So that means I'm decrease the distance between the 2 points to literally 0. And this h is the distance between the 2 points. And this is what it is. And this is what, this is again the slope. y2 minus y1 over x2 minus x1. Algebraically, this is what it looks. Make sense?
So does instantaneous rate of change, does that just mean like the
the derivative.
Okay.
Instantaneous rate of change is the derivative. You know what? When you're driving the car, Romel, any confusion?
No.
All right. When you drive the car, so there are two scenarios. One is, you started from your house and let's say you went to a point, to your school. And after you reached the school, I said, okay, what was your speed? So what you'll say, okay, I started at 8 a.m. I arrived at my school, let's say, for calculation purpose, 9 a.m. So I traveled for 1 hour, right? And the distance I covered was 25 kilometers. So 25 distance over time is the speed, right? So you started off, let's say, if I have to plot the graph, you started off here and you ended here. So let's say this is what it was, right? And this is distance and this is time. So you started at 0, 0, and let's say your time was 1 hour, if this is an hour, and this point is 25. So if I say, okay, tell me what was your speed? So you'll say, okay, y2, so that's the first point. I'll say 1 comma 25, and that's the second point, 0 comma 0. So I'll say, okay, y2 minus y1, 25 minus 0 over x2 minus x1, 1 minus 0. The answer is 25. So say 25 kilometers was my average speed. I've calculated the average rate of change. Yes, Romel?
Mm.
But if I ask you, what was your instantaneous rate of change? You can't tell. You can. Whenever you are driving and you're looking at the speedometer, the number that you see is actually instantaneous rate of change. That's the speed at that fraction of second when you've looked at the dashboard. And it keeps changing. Right? You break it down, it's going to come down, you're going to press the throttle, it's going to go up. It keeps changing. So whenever you want to see the instantaneous rate of change, look at the dashboard, see the speed and say that's the, for example, if you're driving 60 kilometers, 62 kilometers an hour is the instantaneous rate of change at the point when I've just seen the dashboard. That's broadly the difference between the two rate of change. So the speedometer, when you're looking at it, the speed that it's showing is the derivative. But then when you reach at your school or whatever point you want to, and you're trying to calculate how much time it was and how much distance over time is speed, that is the average speed. Does that make sense now, right? Oh, good. Now, for the ease of calculation, so shall I take this off, please?
Yeah.
For the ease of calculation, the first principle is quite a challenge to solve. So if I were to find the derivative, let's say we find the derivative using first principle.